Okay, the next problem is a fluid problem, and we're told that we have a tube that has a diameter d1, and then it shrinks to a diameter of d2, and we know there's a velocity v1 going into the bigger diameter and a velocity v2 coming out of the second diameter. And one tool we have to begin is the continuity equation, which says that the rate flow is constant, and the rate flow, if you remember, is the area times the velocity, so A1 V1 has to equal A2 V2. And since we're given diameters, we can say that the area is pi d squared over 4, so we have pi d1 squared over 4 V1 has to equal pi d2 squared over 4 V2, which means that V2 is going to equal d1 over d2 quantity squared times V1. And if we plug in these values that we know, we're told that the first diameter is 3 centimeters. The second one is 0.3 centimeters. Notice we didn't have to change to meters since it's a ratio of the same units. And then the first velocity is 0.65 meters per second. And if we do this, we find out that the second speed is 65 meters per second. And we anticipate that because it has a smaller diameter, so to keep the flow rate constant, it would have to go faster. And now if we use Bernoulli's equation, then we can find the pressure that we're asked to do. And notice that they tell us it's a horizontal tube, so there's no change in length, in height. So this means that P1 plus 1/2 rho V1 squared has to equal P2 plus 1/2 rho V2 squared, where V1 could be the pump and P2 could be at the nozzle. And solving for P1, we would get this is P2 plus 1/2 rho, and then if we take the 1/2 rho as a common factor, we get that P1 equals P2 plus 1/2 rho V2 squared minus V1 squared. P2 is coming out of the nozzle, so that's atmospheric pressure, which is 1.01 times 10 to the 5th Pascal, plus 1/2 rho is the density of the fluid. In this case, it's water, so 1,000 kilograms per meters cubed, times the second velocity squared, so that's 65 meters per second quantity squared, minus the first velocity, which is 0.65 meters per second quantity squared. And if we do that, we will get about 2.21 times 10 to the 6th Pascal. And if you want to change this to atmospheric pressure units, then we can use the conversion factor that says that 1 atm, or atmospheric pressures, is 1.01 times 10 to the 5th pascals, which gives us about 22 atms. Either answer would have been accepted.